Good day and welcome to the Geo-Institute 4th Annual Live Streaming Web Conference. Today's topic will be embankments, dams and slopes, and the program facilitator is Tim Stark. This is an audio web conference. You will hear the presentation through your computer speakers, and there will be a PowerPoint presentation that will be shown throughout the meeting. You can ask a question through the online web conference tool at any point during the session by clicking on the Ask Question button on the left of your screen. Type your question into the box and hit the Send button to submit your question. I'd now like to turn the floor over to today's facilitator, Tim Stark. Sir, the floor is yours.
Thank you, Stephanie. Good afternoon, everyone. Thank you for joining our second web conference on embankment, dams, and slopes. These are 3 web conferences organized and being presented by members of the Embankment, Dams, and Slopes Committee of the Geo-Institute. Before starting, I'd like to introduce our gold sponsor for the web conference, which is Keller. The companies of Keller in North America are uniquely positioned to handle the most complex geotechnical construction projects nationwide, including all services in one contract. Keller reduces client risk and ensure all aspects of a project are met on time and on budget. We're grateful for Keller's support of these web conferences. The 4 speakers in our second web conference are shown on the screen. Dr. Shewbridge will lead us off, and then Binod, Tiwari, Farshid, Vahedifard will be our 3rd speaker, and I'll wrap up with a presentation at the end. I'll introduce every speaker at the start of their presentation. So our first speaker is Dr. Scott Shewbridge. Dr. Shewbridge is a senior geotechnical engineer and risk specialist with the Risk Management Center in Denver, Colorado, which is part of the U.S. Army Corps of Engineers. Dr. Shewbridge's presentation is titled Undrained Strengths and Long-Term Stability of Slopes. Scott, thanks for joining us, and the floor is yours.
Thank you so much, Tim. Can you hear me all right?
Yes.
Very good. Again, thank you so much for having me speak. Today my topic is undrained strengths and long-term stability of slopes. This is a summary of an article that I submitted to the Geotechnical Journal. It was published in November, and I submitted that as an individual. So today the opinions and information I'm going to present are my own and not necessarily those of the Corps of Engineers, my employer. The objective of my presentation today and of the paper are to promote a better understanding of the interrelationships between SM.ASCE, fully softened, and critical state strength theories and how they relate to traditional Corps of Engineers QR and S methods for evaluating strengths for a variety of loading conditions, most importantly in this topic today, about long-term conditions. My concern is that I believe that there's an error in the Corps Slope Stability Manual and in our levee manual, and I'm trying to make the case to correct those errors in those manuals. Towards that end, I'm going to be talking about these 5 topics: summary of cohesive soil strengths. I'll review SM.ASCE, fully softened drain strengths, and critical state soil mechanics, and how they relate to the original theories of cohesive soil strengths advanced by Casagrande and Taylor. I will then look at the evolution of core slope stability analysis methods, and then I will provide some examples of undrained failures, which suggest that we still have a continuing problem with the methodologies in the core manuals. Finally, I will end with recommendations how to resolve those problems. So, moving forward, starting off with a summary of cohesive soil strengths. First, I'm going to draw your attention to Donald Taylor's book, Fundamentals of Soil Mechanics, which was published in 1948. It's an excellent book. There are still copies of it available used. I've gotten one off of Amazon. I highly recommend it to all geotechnical engineers. In the chapter 15 on the strength of cohesion, there are 2 graphs graphs that I want to draw everybody's attention to. They're very, very helpful in relating consolidation and stress history of a sample or of a soil and its strength, both drained and undrained. The first slide, which is figure 15-4, is shown here. And it's a typical consolidation relationship showing log linear relationship between void ratio and stresses. You can see the linear consolidation path down to stress state B, where the material is normally consolidated. Then that material is unloaded and then reloaded to a state L, where that material is highly over-consolidated with, say, an OCR of 8. We can apply more load to it and bring it back to load level S, and it's somewhat over-consolidated, perhaps an OCR on the order of 4. OCR being the over-consolidation ratio, which I'm sure you all are familiar with. What's very interesting about this plot, and I haven't seen it in any other publication, is Taylor also presents relationships for triaxial test results on this same graph. And you can see dashed lines indicating different factors that you would plot up to develop a Moore circle. And Taylor puts forward several examples that you can look at, and I'll back up for just a second just so that you can see it. He shows examples of how to extend lines horizontally and vertically to evaluate the appropriate parameters. So if I am running an undrained test, during undrained tests, void ratios do not change. And so I go across from my stress state, say it's state L, and I take and extend a horizontal line across and intersect the dashed lines, and those will be the values that I'll plot up for my undrained Moore envelope. If I'm going to look at drained results, in that case, it's stresses which remain constant, and so I extend vertical lines up or down to, again, intersect those dashed lines to find the values to plot my Moore's envelope. And that is what is portrayed in this figure here, figure 15-10. And so for the material that was highly over-consolidated at sigma L prime, what we see is that the undrained strengths are significantly higher than the drained strengths. And this is an interesting presentation of Moore envelopes because we have two different forms on the x-axis. The drained envelope is plotted with effective normal stress on a failure plane at failure. The consolidated undrained envelope is plotted with effective consolidation pressure just prior to loading. And again, the over-consolidated soil has the undrained strength substantially higher than the drained strength, whereas the normally consolidated soil, sigma B prime, the undrained strength is substantially lower than the drained strength. This same relationship is found in Skempton's work on pore pressure parameters. And here we see a plot from a presentation by Bishop and Bjerrum, 1960, of results of a sample tested at different over-consolidation ratios, and we see variations in the value of A sub F, the pore pressure parameter associated with application of deviator stress. And so for this material, when the over-consolidation ratio is between 1 and about 4, A sub F is positive, indicating that in undrained loading, this material will generate positive pore pressures. For OCRs greater than 4, A sub F is negative, and the sample will generate negative pore pressures during shear. These are the bases of the Corps of Engineers methods for evaluating shear strengths. It's important to understand the consolidation history and important to know the shear drainage. And we have a series of tests, Q, R, and S. Their modern names, which I prefer, are UU, unconsolidated undrained, CU, consolidated undrained, and CD. And we use these methods to evaluate different strengths under different loading conditions when conducting slope stability analyses. Next, I'm going to give an overview of work done since Donald Taylor passed. Donald Taylor was Unfortunately, we lost him very young. He was 55 years old in 1955 when he passed. And his work was continued on by other researchers. The first I'm going to look at is S.M.ASCE, continued on at MIT by Chuck Ladd and his colleagues. And in S.M.ASCE, many people are aware that some of that work was developed as cooperative research supporting the Corps of Engineers. Here we have two reports, one looking at the Atchafalaya levees in Louisiana, and another looking at direct simple shear tests conducted on Atchafalaya levee foundation clays and clays from other parts of the world. From this work, we end up with a very well-known S.M.ASCE equation, which relates the undrained strength ratio, S sub U over sigma Vc prime. That is equal to an undrained strength ratio when the OCR is equal to 1 multiplied by the OCR raised to an exponential power. And that is expressed here in these curves. Here we see OCR and the undrained strength ratio. When the OCR is 1, we have the value of the S, and then the OCR to the M is expressed in these curves, these exponential curves going up. In 2008, working on a project for the Department of Water Resources in California, we had a challenge in that we needed to evaluate undrained strengths for 300 some odd miles of levees very rapidly. And a very brilliant young engineer, Juan Perry, came up and recognized that this equation could be rearranged and portrayed in the manner that Taylor presents it in his 1948 presentation. And here you can see the undrained strength envelope as a function of the vertical effective consolidation pressure just prior to shear. And for the material which is over-consolidated, we get this J-shaped curve, which is just the same as what is on Taylor's figure. And then for the materials which are normally consolidated, we have this straight line, normalized type of relationship. So that fits very well, very complementary to what Taylor has done. Next, we'll look at work conducted on fully softened strengths. The first presentation of this was presented by Skempton in 1964 in his 4th ranking lecture on long-term stability of clay slopes. And in this paper, Skempton presents work that he and his colleagues did evaluating slopes which had failed many years after they were constructed. These slopes were generally excavations. They were oftentimes adjacent to railroads, and failures occurred 20, 30, and as much as 50 or more years after excavation. The excavations were advanced in over-consolidated London, and typically they were the London brown clays, which they were somewhat oxidized. They had been over-consolidated by glaciation. Over time, those materials became weaker. And the question was, what was causing that process? So a whole series of slope stability analyses, back calculations were conducted, and the results of those stability analyses were compared to stability analyses using strengths measured from laboratory tests. And what was found is when the peak strengths were used in the analyses from the laboratory, you would get overestimates of the factors of safety. And what was found from the back calculations is that long-term strengths were considerably lower than what you could measure in the laboratory at the time. Now, when these analyses were first conducted, it was presumed that no negative pore pressures remained in the slopes, either from the excavation or from shear of the materials. Unfortunately, that was not correct. And so in 1977, in the International Conference paper, Skempton presented what some people refer to as his mea culpa paper, in which he acknowledges that there was, in fact, negative pore pressures still existing in those clay slopes, despite their fissured nature. And when those negative pore pressures were included, that resulted in somewhat of an increase of the fully softened strengths for those first-time slides. So the strengths are still lower than what was measured in the laboratory, but they were higher than had been considered in 1964. And also, it was found that the best way to estimate those drained long-term strengths, the fully softened or critical state strengths, the best way to evaluate them was to conduct laboratory tests on normally consolidated, not over-consolidated material, but normally consolidated material sheared at rates slow enough to allow all positive pore pressures to dissipate in the laboratory. And we end up with very low friction angles, higher than residual friction angles, and oftentimes little to no cohesive intercept on the y-axis. Next, I'm going to present a very quick summary of critical state soil mechanics and how these relate to the previous methods. And in the United States, not so many people have been familiar with the work of Schofield and Roth, based in large part on work conducted with Professor Roscoe. But again, well, I don't actually recommend people get this book. It's a tough one to read. I found Atkinson to be easier to understand, but it provides an overview of the critical state concept. And that, stated in its simplest form, the critical state theory holds that plastic shear deformation of a soil will tend toward and then proceed under unique combinations of mean effective stress and void ratio. And those unique combinations are called the critical state. What does that mean? That's not exactly intuitive directly. So I put together these plots back in 2013 to help engineers that I'm working with understand. And it shows you a set of relationships for void ratio and effective stress, shear and volumetric deformation, stress strain characteristics, and dilation or contraction characteristics. And for the drain materials, if we take two samples of soil, same soil, but they're at different states of overconsolidation, but at the same initial effective stress, when we shear the normally consolidated soil under a drain condition, the material will contract during shear, and it will proceed towards the critical state, that unique combination of void ratio and effective stress, and it will stay at that critical state, yielding a drained strength, as shown by the green arrow on the stress-strain diagram. The dense material, the overconsolidated material, will tend to dilate during shear. Effective stresses will stay the same. There will be work overcome in dilating, and so you'll get a peak strength at the maximum rate of dilation, and then as dilation diminishes, you will then reduce in strength down to that drain strength equal to the normally consolidated drain strength. So that is the drain result. Complementary undrained result, take that normally consolidated material and we shear it. When it shears, it wants to consolidate but cannot, and so positive pore pressures are generated. The effective stresses go down, and the strength is lower than the drain strength for the same material. The opposite is the case for the overconsolidated material. This material, when it shears, generates negative pore pressures, increasing the effective stresses, resulting in higher strength. Together, these graphs essentially portray what is shown in the fully softened paradigm for the drain strengths and the Shanset paradigm for the undrained strengths. And this leads to a situation when I'm working with oftentimes geologists on problems. I try to explain that there are essentially 4 different strengths that you have to consider. For soft materials where the OCR is greater than, say, or less than, say, 2 to 4, your drain strength will be higher than your undrained strength. For stiff materials, your drain strength will be lower than your undrained strength. I also need to point out often that it is difficult to confirm drained conditions will occur in the field for soft materials. And for that reason, rarely do I end up using drained strengths for normally consolidated materials for evaluating strengths. It is nigh impossible to prove absolutely that you will be able to dissipate all positive pore pressures generated during shear. So you end up essentially with 3 different types of straight: Shanset, fully softened, and then temporary strengths that you might consider, and I'll sometimes use those when doing construction excavation. Putting all of these concepts together, overlaying them on Taylor's figure, we end up with this coherent, consolidated overview of fully softened, Shansep, and critical state theory. When the OCR is greater than 2 to 4 and the material is denser than the critical state, the material will tend to dilate during shear, and you will end up with the drained envelope being controlling. That would be the fully softened case. For materials that are lightly over-consolidated to normally consolidated with an OCR between 2 to 4 and 1, in that case you would have the Shansep undrained envelope controlling, and you would use the form of the equation where the OCR is raised to the exponential power. And then finally, for the normally consolidated materials, it is the undrained envelope that will be controlling. So we end up with this composite failure envelope with the lowest cases being shown by the heavy line here. Okay, that seems consistent. All of these theories seem to complement each other. Where did this come from? Here is a composite failure envelope. It appears similar. We have the drain strength lower than the undrained strength at this area, but up here where we have the S strength and the R strengths, the R strength being undrained, we then show a design envelope which is halfway between the two. Where did this come from? Now go into an evolution of core slope stability analysis methods and give you some understanding of that. In 1945, the Corps of Engineers published the Civil Engineering Manual, and it has a chapter in there in soils investigations. It does not contain any information on how to calculate slope stability, but it does present the slope stability charts of Taylor and the method of Fellenius and some results from the Fort Peck investigation. In 1952, that manual was supplemented with this chapter on stability of slopes and foundations, which does include quite a bit of different methods for evaluating slope stability, but it includes almost no information on how to evaluate drained or undrained strengths. What it does contain, though, is a reference to a 10th progress report on Cooperative Triaxial Research Program by Don Taylor. That report, and that's an incomplete reference, that report is summarized by Professor Rutledge, and it's a summary of the Cooperative Triaxial Research Program of the Corps of Engineers. It was a cooperating program put together with Harvard, directed by Arthur Casagrande, and MIT with Dr. Donald Taylor. And in the Rutledge report, he summarizes Arthur Casagrande's working hypothesis for cohesive soil strengths. And you'll see in here the description of quick tests, the Q tests, the consolidated quick, QC, which were later called R tests, and then the slow tests. And here is that working hypothesis. This is a copy of the report from 1941, and it shows triaxial test results in consolidation relationships for 3 different soils, 3 different cohesive soils. The first one to the far left is a normally consolidated material. The second is a somewhat over-consolidated material. And the third one on the right, which is truncated because I don't have all of the original figure, that is for a highly over-consolidated material. And what you can see is the drained envelopes are these dashed dot lines here. The drained envelopes for each test are about the same. But the undrained envelopes, the solid lines, are very different. The normally consolidated material has a very low apparent friction angle. The moderately over-consolidated material has a higher apparent friction angle. And then on the far right, the over-consolidated material has a much higher apparent friction angle. These results can then be plotted up, and we see on this figure 2 different failure envelopes. We see the drained failure envelope, the S, where we have some amount of curvature at low stresses and perhaps a small cohesion intercept. And then we see the undrained envelope, the QC envelope, which has that characteristic J shape and which is just exactly the same as what we see in Don Taylor's presentation right here. And in fact, I believe that's where this came from. So this information was then codified in the 1960 version of the Core Slope Stability Manual. And what it's said to do is that there seems to have been some disagreement as to which strengths we were controlling. And so engineers were directed to evaluate both for drained and undrained strengths. And then the factor of safety of the slope would be selected as an average of the limiting values represented by these computations. So by the time the 1970 version of the Core Slope Stability Manual was published, rather than going through and calculating all those slope stability computations by hand all over again for both R and S strengths, a decision was made to take the average of the R and the S strengths and use a composite envelope as shown here. So the important thing is this composite envelope is something which was developed as a convenience for computations, but it is not directly related to soil mechanics itself. And essentially that composite envelope is not correct. So in 2003, the Corps of Engineers updated the Slope Stability Manual, and for steady-state seepage conditions, instead of using the R plus S over 2 envelope, we now only use the drain strengths. Unfortunately, that's not correct either. And the reason it's not correct is we make an assumption in this approach that says all drainage occurs, which is not always correct. So, how do we know that? I'm going to show some undrained failures, the most famous of which and the most painful for Corps of Engineers folks to deal with is the failure of the 17th Street Canal during Hurricane Katrina in New Orleans. And in that situation, we had normally consolidated marsh and lacustrine sediments which were subject to undrained failure on loading. And when the levee slopes were loaded, they were sheared into undrained conditions. A full hydrostatic head did develop on the sheet pile wall, resulting in higher forces on the wall and a passive thrust on the marsh and lacustrine materials. Those materials, under a flood loading, experienced undrained loading, and those undrained strengths in all of the forensic analyses were roughly half of what would have been estimated if they had used drain strengths as directed in the Corps manuals. And this suggests that our Corps manual has a problem with it. When we've gone through and done the repairs for New Orleans, we have used undrained strengths for all $14 billion worth of those repairs. And the reason is that it is not proper to assume that there will not be positive or negative pore pressure generation during shear. A normally consolidated material loaded by a flood will generate positive pore pressures if that loading occurs faster than pore pressure, shear generated pore pressures can dissipate, and you have to consider undrained strengths. So, other examples of undrained failures, I highly recommend everybody download the report by Morgenstern et al. On Mount Poly. I believe Tim Stark is going to give us some overview of the Fundao tailings facilities, which are cohesionless materials. Nevertheless, undrained failure is a concern as to whether it's static liquefaction or earthquake-induced liquefaction. Tim will give us some insights about his feelings about that. Just about at the end of the time, my recommendations are straightforward. Return to the approach developed by Casagrande and presented by Taylor. I recommend that engineers use a simple critical state OCR heuristic or rule of thumb, which basically suggests that if your OCR is less than about 2 to 4, undrained strengths will likely be lower and maybe controlling. The OCR is greater than 2 to 4, drain strengths will likely be lower and maybe controlling. And rather than using R plus S over 2, I recommend people use SHANSEP to make more accurate assessments of lightly over-consolidated and normally consolidated strengths. And essentially, this is a copy of Figure 7 in the paper, that is my recommendation for evaluating strengths for long-term conditions. I want to acknowledge two comments that came from Professor Morgenstern. He reviewed the paper for me as a courtesy. I very much appreciate it. He had two concerns, one of which was did not do enough to talk about sensitive clays, native clays that such as you might have around the St. Lawrence Seaway. And I do reference BRM 1973 and do recommend people look at the recompression method when you need to evaluate higher undrained strengths that associated with a sensitive fabric. He also felt that I did not do enough to talk about non-cohesive soils, and I agree with him completely. I decided I didn't want to take on the world of liquefaction gurus in this paper. Unfortunately, the forum papers are only 5,000 words long, and just didn't think I could cover it. I also am not yet to make recommendations on triggering relationships for static liquefaction. So I've presented too much stuff, too much information in too little time, but I appreciate your patience with me as I've gone through. I'll now answer, if I can, any questions that Tim might have brought up, and if you have any other additional questions afterwards, please feel free to contact me.
Great, Scott. Thank you for an excellent presentation, and especially going back to Don Taylor's seminal work. While I'm checking the Q&A, one question I have is, really, you're discussing peak strengths now. Of course, if there's any indication of deformations or prior deformations, of course, you would move to a deformation-based or a post-peak strength. Right?
Yeah, what I reference in the paper but don't have time to talk about within the 5,000-word limit is Skempton's 1985 paper, in which he lays out clearly the conditions where you would degrade from peak to a fully softened to a residual. And similar to as shown in many of your correlations, Tim, generally your residual strengths will be lower with higher plasticity.
Right. Okay. Right now, okay. There is one question here. Scott, are you working on liquefaction conditions as well? And can you send out your paper to John Smith?
John Smith, please contact me directly. I can't send you the original paper because it's copyrighted and you have to download it and pay for it from either the journal or get it offline, but I can send you galley proofs of it. I am constantly working with folks on liquefaction evaluations, and I do think that the things that Tim is presenting and that Morgenstern's presenting, and then the fellow from Australia who's just published the paper on the Fundao, I think that those issues are all important. I myself am not yet ready to make a recommendation for a triggering relationship for static liquefaction. I use Bollinger and Idris and Seed and Ketten et al. For normal seismic liquefaction and triggering all of the time. And when I do that, I end up using undrained strengths, sometimes normalized, sometimes just standard total stress strengths per Seed and Harder. So that's a lot of stuff to say in a very small space. That's a tough question. Please email me. I'd be happy to give you further information.
Great. Okay, Scott, thanks so much for kicking off our second web conference on embankment dams and slopes.
Thank you so much.
Thank you, Scott. Our next speaker is Binod Tiwari. Binod is the Associate Vice President of Research and Sponsored Programs, as well as a Professor of Civil Engineering at the Cal State Fullerton, California State University System at Fullerton, California. Dr. Tiwari's presentation today is titled Post-Fire Debris Flows. Binod, thanks for joining us today, and the floor is yours.
Thanks, team. With the interest of time, I'm skipping the first slide. So before I start with, I would like to acknowledge the work of Dr. Binod. He is an assistant professor at North Dakota State University. Rupert Bernard from my grad student at Cal State Fullerton, Anthony Gonzalez, my undergraduate student at Cal State Fullerton, Basil Habib, undergrad student Cal State Fullerton, Hassim Sonbal from North Dakota State University, and Chris Doolittle from Santa Barbara County Public Works. So these individuals have contribution into this work that I'm presenting today. So the content of today's talk is, first I'll talk a little bit on the loss due to wildfire, and then I'll go into local case, recent wildfires in California, and this presentation focuses more on the recent Montecito wildfire induced debris flow case, and I'll show you a few field conditions at Montecito, and then I will talk a little bit about our lab tests we did on those soils, and I'll summarize. If we look into the loss due to wildfire in the country, in addition to structure we lose, we also lose firefighters. So if we look into the records for past 4 or 5 years, over 10 firefighters lost their life in dealing with containing those wildfires, and over thousands of structures have been burnt, and this is a critical issue in Southern California. So if we look into the record of left side I have is the total number of fires in thousands, and the right side is the total the acres of millions of acres of the land burned by wildfire. So if we look into the numbers, although there are waves, we could see we get about 80 to 90 wildfires consistently a year, and then we lose 6 to 8 millions of the area, the grass area due to the wildfire. So if we look into it, you see, although the numbers are pretty much consistent in past 20 years, the total acres of the burned area is increasing significantly in recent years. So this is a little dense figure, but what I'm trying to show in this figure is these are the wildfire records in California. So California is one among the states in the U.S. that is hit by wildfires and then wildfire-induced debris flows. And if we look into the case this year, already in 2019, this is less than, I have to add a few more figures on that, but we already had many wildfire incidences in Southern California in this year itself. So this table shows the variation in total incidences we have in past 5 years, and they're about in California that's about 8,000 wildfire incidences per year, and the total area burned is 3,400 up to 7,000 square kilometer. In 2018 we got more area burned due to wildfire, and then we lose millions of dollars, and even last year we lost $3.5 billion due to wildfire, and 2 years ago we even lost $18 billion due to wildfires, and we lost over 100 people in 2018 due to wildfire. So this clearly tells that wildfires are critical in Southern California. And because of that, our study started after Montecito wildfire. It was in Santa Barbara. So we started getting database, and USGS did pretty good job in compiling the wildfire database. And there are a few more articles that we can get in the literature that that added more into the database of wildfire cases in the world. But this we collected about 185 events in 7 U.S. states, starting from 1928 through 2018. And if you look into the database, you can clearly see that the orange portion is in California. So 58% of those wildfires are in California, and the states followed by California are Colorado and Montana. So these are the places where we saw more incidences of wildfires. So we made, you see, the total burnt a chart where y-axis is total burnt area in acres, and then x-axis number of debris flows. What we could clearly see is the Californian wildfire, the trend is totally different than the trend for other states. So in California, there are not that many debris flow incidences, although the number of debris flow increased with an increase in the burnt area. Right? For the same number of burnt area, burnt by wildfire, other states have more number of debris flow incidences compared to California. That's mainly because of the amount of rain that we are getting in California is significantly low compared to other states, such as in Colorado. So this figure shows the number of previous wildfire events prior to the debris flow event. So we tried to see if there is a correlation between the number of wildfire incidences in the area and the debris flow events. And there was not direct correlation on it, but majority of them had, if 43% of the debris flow incidents happened when they had more than 15 wildfire incidences in those areas, while 27% had only 4 wildfire incidents in the area. But although there was not direct relationship, what I could tell with this is more number of wildfire incidents in the same area, there is strong likelihood to have more debris flow incidents, debris flow cases. So now let's talk about the study in Montecito debris flow area in Southern California. This is the Google Earth map, where you can see with those gray patches are the area affected by the Thomas fire. Thomas fire is one among the largest wildfires in the country. In the Thomas fire it burned over 300,000 acres of vegetation covers, and the area was in Santa Barbara and Ventura County in California. The fire started on December 4th, 2017, and all the way to January 12th, 2018. By that time, they were contained, and over 1,000 buildings were damaged with the wildfire, this Thomas fire. The total damage actually exceeded over $2.2 billion. And the worst thing happened during that Thomas fire was, before the fire was even contained on January 8th, and 8th and 9th, there was a big rainfall incident, rainstorm, and because of that storm, the debris flow occurred at Montecito, at Santa Barbara County, and that killed. Now, the new statistics is 23, but there are different, contradicting statistics. So the debris flow incident killed over 21 people and injured over 150 people. And the debris flow incident itself caused a loss of over $200 million loss of property. Then there were over 60 residential buildings completely damaged, and over 450 residential buildings were partially damaged. There 8 commercial buildings got complete damage, completely damaged with the debris flow incidents, and 20 buildings were partially damaged. Commercial buildings were partially damaged. So major highway 1 is fully covered with debris and was shot for weeks due to the debris flow, and the highway got 10 to 12 foot deep debris flow, and if that debris even went to ocean, and the area evacuated. The area was completely evacuated after the incident. There was no utility service, and then waterways for the bridges and culverts were completely blocked. Many of them were completely blocked. I'll show you a few pictures of the incidents. And the worst thing was because of those incidences, there were so many security issues in the area as well. So the total estimated intensity of rainfall at short-term intensity of rainfall was 2.5 millimeter per hour for 20 to 30 minutes, and the total hourly rainfall at that time before the incident happened was 125. 24-hour rainfall was 125 millimeter. There was a rainfall for more than a year, more than a day, continuous rainfall, and this clearly shows that at Montecito the intensity of rainfall was pretty high compared to the other areas. This is the photograph of the creek. This is a left side is Cold Spring Creek in Montecito. Right side this bifurcation is Hot Spring Creek in Montecito. This is the picture before the debris flow incident, and this is the picture after the wildfire and after the debris flow incident. So, you can clearly see that the creek was full of those large-sized boulders. And if we look into the look into the let me go back. I'm having trouble with animation. So this is the close view of that the Cold Spring and Hot Spring creeks, where you can see the creek is full of debris. And if you look into the this is an overview of the debris flow area. So on your left, it is Hot Spring, Cold and Hot Spring creeks. And then the big one you can see at the middle is the San Isidro Creek, and on two springs, two creeks you have on the right side are the Buena Vista Creek and the Romero Creek. So these are the creeks that were affected by debris flow, and you can see the debris flow mass. This is the picture from the picture you can see on the left, the Hot Spring and Cold Spring creeks. If we look into the highway, so highway was fully blocked with those debris flow, and you can see the mud flow, the content, soil content of the mud flow that reached to the highway were mostly fine soils, but the one that went to that were in the creek area were big boulders. So you can see on the picture on the right, this is at the middle, you can see that debris catch basins or debris retention basins, and those retention basins were full with the debris, and then there was overflow of the debris all the way to the river, to the ocean through the highway. So that you see there were large size boulders. Some of them even were 6 or 7 meter diameter boulders, and there were those boulders were hitting the area. And the worst thing was there were many trees and tree trunks. They were blocking the culverts and waterways and the bridges like that. You could see, and then those combination of those big boulders and the tree trunks blocked the bridges, and then that blocked the path of the flow, and the bridges were many bridges got washed away due to the debris flow event. And like those houses, some houses were still okay, they're away from the debris flow, but many houses got completely damaged due to the debris flow. And for your information, houses in that area is very expensive. That is, very well, high-end. I would say high-end area, and the houses are very, very expensive there. And you see, those bridges. Some of the houses got saved because this is one instance where bridges were the waterway of the bridge was full of those tree trunks, and then those tree trunks actually diverted the debris flow from the creek to the community, and then you could see these houses were not in the direct hit from the debris flow, but because of the diversion from of the debris flow from the due to the tree trunks, those houses got hit. So this house was completely buried with debris flow. And some area, while the debris took the completely washed the bridges away, the gas lines were also got broken, and then because of that there were a few fire incidences in the area. So the culverts were fully, you can see the deposit, debris flow was deposited all the way to the road here. You could see that, and then the culverts were fully blocked with the debris flow. That this picture was after the culverts were cleared, and you could see the situation. This is the picture I got from Chris. The culverts were fully covered with blocked with debris. And this is the situation even after the 3 or 4 months after the incident. So the mountain was. This is the impact of the wild Thomas fire. You could see, and my big worry is, if this situation remains, the area has a strong potential to have more debris flow in future. So this is the same picture that I showed before. This is the actual affected area. And what we did was we collected the rainfall data from a few stations near the wildfire area, and out of that, I'll be presenting the data from two rain gauge stations. There is a typo on rain here, RAIN, and so if we look into the intensity and duration of the rainfall, this is out of 185 total events we saw in the history. Then we can clearly make the rainfall intensity duration threshold. For the debris flow incidences after the post 2010, the intensity duration curve moved a little upwards, and for before the 2010, the intensity duration curve moved a little downwards. So I don't think that has a big implication on the issue. So what I did was I ignored one point here, and we made the intensity duration curve covering all 185 debris flow incidences. When we plot the Montecito intensity duration for the total storm duration, then those two triangles you can see on your right fall right at that point. So it was obvious that Montecito was getting debris flow with those incidences. Now, when we compare the Californian intensity duration curve, that's the upper red line, versus the intensity duration curve in Colorado, we could clearly see that California required a little more intensity of rainfall, intensity of rainfall for the same duration to trigger the debris flow compared to Colorado. So if we look into the rainfall data from those stations we got from this station, this close to the main debris flow incidence site. So what we could see in 2017 January rainfall was 2018 January rainfall was way less than that in 2017. So it clearly shows that the wildfire was responsible for those debris flow incidences. So when we look into the incidence for the data for the other site, other rain gauge data, same situations. 2017 rainfall was way more than the 2018 rainfall, although the debris flow incidence occurred in 2018. So when we looked into the data during those 2 days of rainfall, what we could see is there were few cases where for 20 or 30 minutes there were 12.5, half an inch per hour of rainfall incidences, and then debris flow got triggered at that particular point. And if I plot the data, x-axis here is the duration of rainfall, and y is the intensity of rainfall, and the upper solid lines are the intensity duration threshold for different part of the world, not for the wildfire-induced debris flow. It's for debris flow incidences, the rainfall-induced debris flow incidence. And the left side, the broken line you can see is the case for the USA. And when we plot the intensity duration data for Montecito for that short duration rainfall, that is hitting exact at this point. So it was obvious that the rainfall intensity and duration during that time was large enough to cause debris flow in Montecito area. So after the incidents, we collected soil from the site, and we collected soil from we collected the finer portion of the soil from the site, and we also collected the S.M.ASCE deposit from the site, and this is grain size distribution of the finer particle size from the debris flow area. The liquid limit of the soil was about 42%, plasticity index was about 5. And we conducted ring shear test to see what was the residual friction angle for the soil, actually original soil, the fine portion of the original soil from the area, and we also conducted ring shear test to see the residual friction angle of the S.M.ASCE deposit, because there was a thick S.M.ASCE deposit throughout the area. And what we could see was the residual friction angle of the S.M.ASCE deposit was only 4 degrees, while the residual friction angle of the base soil was about 23 degrees. This clearly shows that the S.M.ASCE deposit has a lower friction angle, and when the parent soil, when the landslide or those slide events occurred at the top of the source area, and this S.M.ASCE deposit helped to increase the velocity of the debris mass downwards, downstream side. And we also conducted we were not able to get enough soil from the sites to run the laboratory model, but what we did was we created slope similar to that soil we found from the site, and then we we prepared the slope at the density similar to what we got in the field, and we poured in rainfall, and we applied about 30 millimeter per hour of rainfall. This is a little more than what we had in the field at Montecito area. The first model we did was without vegetation. Second model we planted vegetation. It's not the actual vegetation. We just put few vegetation cover. What we did was we varied the density of the vegetation in different models. So we have actually we did 4 different models, and what we found was when there is no vegetation cover, the runoff quantity and the soil erosion increased significantly, but the seepage velocity decreased because of the increase in runoff. On the right, when we have the entire area covered with vegetation, what happened was, you see, runoff amount decreased, soil erosion decreased significantly, but because of the rainwater was perceived and then transferred back to the slope, slowly the seepage velocity increased. That's what we found. So with this, with the interest of time, I would like to summarize what we found from these studies. Was wildfire causes loss in vegetation cover and a significant desiccation of soil to reduce the soil permeability and increase the surface runoff and soil erosion. And ground surface covered with the S.M.ASCE actually makes the ground hydrophobic to elevate the problem. At the same time, the friction angle of the S.M.ASCE is so low that will help the debris mass to slide down quickly and to increase the velocity and even acceleration of the debris mass, and that increase in acceleration caused significant damage to buildings and bridges. The wildfire causes significant reduction in threshold rainfall intensity duration to trigger the debris flow that you could see in those intensity duration threshold curves. So our study actually shows that increase in runoff amount and the soil erosion and the reduction in the shear strength, specifically for the ash deposit, reduce the stability of the debris mass significantly to increase the acceleration of the mudslide and cause significant damage in the area. With this, I would like to conclude my presentation, and thank you very much for your patience, and I'll take questions if we have any.
Great. Thanks, Binod, for an interesting presentation and an interesting debris flow. While I'm checking questions, what time of day was the main debris flow?
It was in morning. So 1 to 3. It is 1 to 3 a.m. in the morning.
Oh, so people were at home. Yeah.
Yeah.
Okay. Under questions, let's see. Nope, I don't see any other questions. So thanks so much, Binod, for an excellent presentation. And I'm going to move on to our third speaker. Okay. Our third speaker is Farshid Vahedifard. He is a CEE Advisory Board endowed professor and associate professor at Mississippi State University. Farshid's presentation today is extreme events and climate change on slopes. So it's a perfect segue after Binod Tiwari's presentation on the Montecito debris flow. So Farshid, the floor is yours.
Thanks, Tim. Good afternoon, everyone. Today I'm going to talk about a little bit about the project that we have been working on to quantify the impact of extreme events under a changing climate on the slopes and earthen structures. Basically, I'm going to start my presentation by posing the question that on this slide, you see a number of events and data, huge landslide and Highway 1, and on the bottom left, actually, that's the mudslide after the same mudslide that actually Binod was talking about. The question is, are they rare events or picture of the new normal? Are those just events that we have to expect them every 10 years, every 20 years, or we are seeing more and more those type of extreme events? And on the right, actually, we see the burned area on the top right. You see the burned area in different, years. As you can see, the area burned by wildfire is increasing significantly. Actually, from 2006 to 2015, the area burned in the western United States is pretty much equal to the size of the state of Florida, which is huge. At the same time, as you can see on the bottom right, basically not only the burn area is increasing, the maximum wildfire actually elevation is also increasing, which means that wildfire is going up and up to higher elevation, which can have several consequences for us as geotechnical engineers in terms of landslide, in terms of slow stability, in terms of mudslide. So that's the first question that we need to answer. Are those rare events or a picture of the new normal? And if so, are we prepared to address those events? Before going further, just let's look at some numbers, some facts. Despite controversies over factors, triggering factors, all recorded observations consistently suggest that there have been noticeable changes in the frequency and intensity of natural disasters and climatic extreme over the several decades. Just to give you some numbers, just to put this in perspective, In the United States, from 1980 to 2019, over the 40-year period, we have had 254 weather and climate disasters where we have had about 1 billion or more losses. So we have had over $250 billion events over the past 50 years, over the past 40 years. And the interesting part is 2019 is the 5th consecutive year that we have had so far 10 or more billion-dollar disasters. Even more interesting is to know that over the past 40 years, we have had 9 years with 10 or more billion-dollar disasters. Out of 9 years, we have had 8 of them in the past 9 years. So we can clearly see that the number of billion-dollar disasters is increasing. So those are facts, those are numbers, and some more geotech-related data. We have had about 1.6 to 3.2 billion dollar in annual losses due to landslides, and this number is increasing also based on the USGS data. Those are directly related to climate change. What I want to say up front is, in this presentation, I don't mean to pose or force that climate change is going to worsen, losses. What I'm saying, what I'm trying to present here is we have to take a scientific engineering approach to quantify the impact. The impact in some areas can be more losses, in some areas may not. So what I'm saying, it's a scientific problem, it's an engineering problem, and we have to take an engineering approach to address this problem. So with that, and those are some other numbers that you can see here. For example, in this figure, you see the increase in the amount of very heavy precipitation in the United States from 1958 to 2007. In average, in the country, we had over 20% increase in the amount of very heavy precipitation. In some areas, like in Northeast, it has been as much as 67%. In some area, like in the West, it was about 9%. So those are recorded trends. At the same time, we have model projections for future events, and there's uncertainty and variability on those models, but pretty much all of them, they suggest that we will see a similar increasing trend in the frequency and severity of extreme event in the future. When I say extreme events, I'm talking about extreme precipitation, I'm talking about flooding, I'm talking about tropical cyclones or hurricanes, drought, waves, and those are some examples that we can think about from a geotech perspective and consequences. So let's look at some interaction between an earthen structure or slope with climatic events. This cartoon is trying to kind of illustrate some potential consequences. When we are talking about more extreme precipitation, what would be the consequences? When we are talking about drought, what would be the consequences? If we are talking about more wildfire, Binod's presentation was a great example to see that if there is a wildfire, there will be consequences from geotech perspective. And in most cases, those events are not isolated. They will act like a toppling domino, and that's what we call cascading events. California, they had a 5-year drought season, and so they're more vulnerable to wildfire, and they have more and more wildfire. And after wildfire, if there is a wet season or like heavy rain, it's a recipe for like a next mudslide or landslide. So as you can see, it's a complicated problem. You are dealing with a chain of events that they act on top of each other. So what will be some more detailed explanation about those climatic change features that we discussed in terms of their fundamental impact on geotechnical properties and some practical impact. When we are talking about increased temperature, it will mean that we will have high evaporation rate, will expose the soil to basically to higher oxidation of soil organic carbon, and we will have snow, ice, and permafrost melting. From practical perspective, it will increase suction. It can cause more desiccation cracking, more shrinkage, and land subsidence. Or the same thing that we can talk about as we discussed about that. For example, for intense precipitation, the practical impact is it's going to cause rapid change in suction and can wash out suction, leading to basically some quick failures in slopes and earthen embankments. As we know, pore water pressure plays a critical role in the majority of failures in the slopes and earthen structures. Or we're talking about sea level rise. When we are talking about sea level rise for all structures dealing with sea level, it will induce earthen structure. It will induce higher pore water pressure and also will expose the soil to more wetting, which will also increase basically the possibility of shear strength reduction due to loss of suction, or also increase basically the possibility of the risk of piping or overtopping or internal erosion. So these two tables that I have here, I'm not going to go through all the details, but in these two tables, we try to summarize the key impacts of climate change features on slopes and earthen structures and some potential failure modes induced by those climate change features. And those are basically, for each of those, we try to compile a number of case histories to support the statement for each. And I added the citation at the bottom of the table. If you're interested, I'll be happy to send you more details or the paper if you're interested. Then, what we are going to do from a geotech perspective, we are talking about higher temperature. We are talking about, higher precipitation. And we are talking about a combination of all these, events, like a cascading event, combined effect. What will be the consequence for us? I would say for us, from a geotech perspective, it's interesting. It will pose a new class of problems. We are dealing with, I would say, complex problems. In most cases, posing, multi-physics problems in variably saturated soils and rocks. It's a very interesting problem from a geotech perspective. In the face of climate change, we have more extreme precipitation. What does it mean? We have higher hydraulic loading and a more transient condition. And then we know that it's pretty common to see dry and wet seasons, a cycle of drought, wet season. And now we have more severe or more frequent dry and wet seasons. So from a soil perspective, we are dealing with a multi-physics problem in variably saturated soils and rocks. At the same time, we need to get some input from hydrologists, from climate scientists, from risk analysis. So that's a very interesting and challenging problem to have. But then there is a problem here. This is not a classic geotech area. That's the main problem that actually, I would say, has prevented the geotech community to play a key role in climate adaptation, problem. Address this problem, I think the key is to collaborate, to go outside basically or classic core area of geotech and work with other people from different disciplines. Is by definition, this problem is a multidisciplinary problem. We have to work with people from climate science, hydrology, climatology, data analysis, remote sensing, and of course geotech. And there are more, of course, but if we can work all together, we can contribute to having climate resilient infrastructure. That's the final goal, to make sure that our infrastructure, our communities communities are safe against extreme events under a changing climate. With that in mind, I've been working on a collaborative project supported by NSF. If I can go back. The title of the project is Resiliency of Geotechnical Infrastructure Under a Changing Climate, Quantitative Assessment for Extreme Events. In this project, we are trying to actually answer 3 key questions. And I think those 3 questions are the main questions that we have to answer for any related project. And those are, what's the impact of climate change or the loading condition on the drivers? What's the impact of changing climate on the rate and variability of extreme events? That's the first thing. The second thing is, what's the behavior of soil under such thermo-hydromechanical processes imposed by climate-adjusted extremes? And then once we have understanding about those 2, then we can quantify the effect of climatic extremes on short-term and long-term behavior of geotechnical structures. So if you look at the list, basically what we are trying to do here, number 1, we are trying to quantify the impact of climate change on demand. Number 2, we are trying to quantify the impact of climate change on supply. And then in number 3, we are taking advantage of findings from number 1 and number 2. Now we are taking those in a structural scale analysis simulations to see the impact on short-term and long-term behavior of geotechnical structures. In the rest of the presentation, I'm going to present 2 case studies where we use this approach to basically study 2 problems. The first case study is to look at rainfall-triggered landslides for a slope in Seattle, Washington. As you know, landslide is a major issue in several regions in the world, including in the U.S. Just to give you some numbers, as I said, in the U.S., just landslides cause about $1.6 to $3.2 billion of losses per year. And landslides kill about 25 to 50 people per year. And the number is over thousands in the globally, if you are talking about, number of people killed by landslide globally. One thing that I wanted to say is there has been 20% increase in the global number of fatalities due to landslide in the last decade. So that's something that we need to definitely consider. In the U.S., we have landslide-prone areas along the coast in California, Oregon, Washington, and also hilly regions in the eastern United States. And of course, we know that rainfalls and earthquakes are 2 major triggers for landslides. In this study, what we did around Seattle area, it's a very landslide-prone area. We selected a slope, and we said, let's look at the impact of climate change on triggering factors, which is rainfall, extreme rainfall. If we can quantify the impact of climate change, use historical data, and also use climate models to project extreme precipitation patterns for future, and then use those 2 patterns in a set of fully coupled hydromechanical simulations to quantify the impact of climate change on hydromechanical response of that slope. So that's what we did in the first case. So in order to basically quantify the impact of climate change on extreme precipitation patterns, we use intensity, duration, frequency curves of rainfalls. We use 2 sets of IDF curves, baseline using historical data versus projected, which are IDF curves obtained for using climate models. We use several climate models, and for projection of those, and we use extreme value analysis for those to obtain intensity, duration, frequency curves. which means intensity of rain for different duration under different recurrence intervals. And for future IDF curves, we use the non-stationary extreme value analysis approach. Non-stationary means that in most cases, people use the assumption that the statistics of extreme events will not change in the future. But the data, recorded data, shows that we cannot extrapolate the historical data to find the future data. And the main impact of climate change is to change the statistics of extreme events. So to consider that change in the statistics of extreme events, we use a non-stationary framework. And what we did, we used that framework to find IDF curves for several regions in the country. And you see on this map that we looked at, as you can see, we looked at more than 10 points for around the country. And we, using those, we could find IDF curves for different regions. What we found was basically in this figure, what I'm showing is percent change in extreme precipitation intensities between historical and future climate projection for different storm duration. So, for example, I'm showing here 4 different locations, and what we saw that was extreme precipitation can increase up to 20% or more in different locations that we examined. So, for example, you see percent increases in like San Diego, Denver, Washington, D.C., Orlando for different storm durations. And we'll look at different, recurrence interval, 25-year event, 50-year event, 100-year event. So that was the impact on intensity. The impact is not only on the intensity, it can be also on the frequency. So we also look at the impact on the frequency, and something that we noticed was extreme precipitation can be twice more frequent in the future. And here you see it's not easy to distinguish the curves on this figure, but what you see here, you see IDF curves for different locations. Blue lines show the median of historical IDF curve or baseline IDF curve, and the red lines show the median of projected future IDF curves in different locations. Depending upon the location, you see different changes. But what I wanted to say was, the summary was, we project to see 20% more increase in intensity and twice more frequent extreme precipitation in the next 50 to 100 years. Then what we did for the selected study area, which is a slope in Seattle, we built a finite element model and using a finite element software package. And you see the slope and you see the input parameters. I'm not going to go through those parameters. And at the bottom, you see the IDF curves that we use. We see IDF curves for different return periods, and basically for baseline and projected IDF curves. And we use different scenarios to project for future. Conservative scenario, RCP 4.5, or more aggressive scenario, RCP 8.5. And then we implemented those precipitation data as hydraulic loads to analyze the slope that we had. What we did a fully coupled numerical modeling. At first, we ran a steady-state seepage analysis using annual rain in the area to generate initial conditions. Then we applied the rainfall data for 7-day precipitation extreme events. And we ran transient seepage analysis. And after that, we again we got back to kind of like a steady state to also consider post-extreme event behavior of the slope. And we use shear strength reduction factor, which is commonly used to represent factor of safety in finite element simulation of slope. And at the bottom of the slide, you see shear strength reduction factor for different duration. And based on the result, the most important basically conclusion from this first case study that I wanted to, if I can go to the next slide. The most important conclusion that I wanted to draw for the first case study was we have 3 cross-sections in the slope, and we'll look at the change in strength reduction factor. When I say change, I mean by comparing the results from historical baseline IDF curves versus projected future IDF curve. And as you can see in this figure, we got pretty substantial change in strength reduction factor, which means that if we use historical data, rainfall data, we can significantly underestimate the impact of extreme precipitation. So as you can see in different locations, we had Section A, Section B, and Section C, we had pretty substantial change in strength reduction factor, which will basically explain the impact of climate change. The next cases that I want to present is modeling Sherman Island levee under compound flooding. Quickly about compound flooding, basically we know that this sea level rise has been an issue, emerging issue, and there have been a lot of discussion about sea level rise. And this sea level rise will reduce the gap between high tidal datum and flood stage, and also reduces also the pressure gradient to the ocean, and it will ease the tide surge wave propagation stream. When we are considering a stream system, there is this interaction between coastal water level and river flow, which will both together will basically control the surface water level. So, which means the flood probability. So, when we are talking about these factors, we are talking about multiple factors that work together. But almost all of the existing flood hazard assessment practices like USGS, FEMA, they only consider one driver of flooding at a time, either like ocean flooding or river flooding. But coastal cities are vulnerable to sea level rise are at risk of compound flooding from multiple drivers, from coastal wave, extreme high tide, storm surge, or river flow. The existing method, they use univariate method, which means that they only consider one driver. They may not accurately characterize flood hazards. What we did in this study, we used a bivariate method, basically which accounts for compound flooding from river flow and coastal water level. So that's what we used, and we applied the framework to find flooding level to Sherman Island levee. Sherman Island is basically a good example to use for compound flooding, because basically, as you can see on this figure, Sherman Island levee basically is located in a delta where tidal and fluvial discharge are at the same order of magnitude. Also, the flooding dynamic is governed by a nonlinear interaction between those underlying processes. During high river flow events, while extreme freshwater influx gives rise to the mean water level adjacent to the levee, it also dampens the tide propagating upstream, so reduces also the tide variability. On the other hand, during low flow period, while the mean water level is relatively lower, damping is smaller, so the tide range is quite large. So as you can see, the interaction of these drivers is not a linear, so they're interacting with each other. So we thought it's a good example to look at this area and see the impact of compound flooding. What we did, we considered 3 flooding drivers: coastal, fluvial, and pluvial. Coastal, I mean mean sea level variability and type. Fluvial, hydrology, the runoff from rainfall, and pluvial, directly from extreme precipitation on the land side. And as I said, for coastal and fluvial flooding, we used the bivariate analysis of peak river discharge and peak coastal water level. While considering the significant correlation between the two, we have 3 scenarios: most likely, Q-dominated, and T-dominated. Most likely is the most likely event, which is associated with the highest joint probability density function. Q-dominated is simulated water level by considering the peak river discharge, and T-dominated is simulated the flood water level scenario corresponding to peak coastal water level. And also we use precipitation IDF curves to find pluvial flooding. And we apply those flood hydrographs as hydraulic loading in a 3-dimensional fully coupled finite element model. This is the finite element model. Dr. Stark used a similar model before for different purposes. We used the same model here. We adopted the same model for our simulation here. Here you see the hydrographs, the flood hydrographs for 3 scenarios that we consider for coastal and fluvial processes: Q-dominated, T-dominated, and most likely. And this is the IDF curves of precipitation that we use for pluvial flooding under baseline and projected future conditions. We use those as input as hydraulic loads in our model, in our finite element model. And we found factor of safety and probability of failure for slope instability. And here you see basically the results for the base case, which is considering only coastal and fluvial processes. And for the sake of time, I'm just going to show the differences, which is the most important part of the presentation, is that when we add the effect of pluvial flooding. When we add the effect of pluvial flooding, you see factor of safety and probability of failure. We use the probabilistic slope stability analysis. When we added the effect of pluvial flooding, just using historical IDF curves, we saw 2 to 18% reduction in factor of safety and 2 to 9% increases in probability of failure. But when we consider the effect of climate change on pluvial, basically on pluvial flooding, IDF curve of precipitation, the trends were even more interesting because considering pluvial flooding under a changing climate decreased factor of safety from 4 to 21% and increased probability of failure from 4 to 14% for this particular case study. So with those, just basically quick review of what we did in these 2 cases. What I was trying to show was we can take a quantitative approach for each site, for each structure, to quantify the impact. Again, I'm not suggesting the impact can be significant or insignificant. What I'm suggesting is we have to take a quantitative approach for each site. We are dealing with a new class of problems, very interesting problem, but the key to address those problems is collaboration with different areas. We need fundamental research to improve our understanding about those extreme events in a changing climate on soil behavior as well as loading conditions. We showed that for 2 cases, for different areas, that intensity and frequency of extreme events are expected to increase. And the key for adaptation, climate adaptation, is to quantify the impact of potential climate change extreme events on the performance of infrastructure. And using historical data, we showed that may underestimate the impact of extreme event on slopes and earthen structures. With that, I'm going to wrap up my presentation, and I'll be happy to answer if there is any question. I also added some of the references at the end of the presentation, related references, and if anyone is interested, I'll be happy to send related references.
Great. Thank you, Farshid, for focusing on extreme events and their impact on embankment, dams, and slopes. This is an area that the Embankment, Dams, and Slopes Committee is working on and actually organizing a specialty conference on for 2021 called Geo-Extreme 21. So I'm checking on the Q&A. I don't see any questions under Q&A, so do you have any final comment before I move on, Farshid?
No, just thank you. And as I said, if there is any question, I'll be more than happy to answer. Within 30 minutes, of course, is not enough time to address all details, but I just wanted to touch base on like key points.
Right. Yep. Okay, thanks, Farshid. I am the last speaker, and my presentation focuses on a dynamic analysis of the Fundao tailings dam failure. With me is Jiale Lin, who helped perform the analyses for this investigation, and hopefully he can help me answer any questions at the end. So the presentation outline is shown here. We'll talk a little bit about the November 5th, 2015 failure, the dynamic events, and our assessment and analysis of the dynamic events, and then a brief summary. So on November 5th, 2015, the Fundao tailings dam collapsed, and there was a significant flow slide afterwards, as you see in these two photographs. 19 fatalities involved in the failure, some on-site and some downstream. The focus of this investigation is the dynamic events just prior to the slide. There were some blasting events prior to these three earthquakes. We analyzed those blasting events and concluded that they did not have a significant impact on the stability of the dam. So we focused in on these three earthquakes, and the important features of these three earthquakes are the time they occurred, basically between 2:12 and 2:16, so there were three earthquakes in 4 minutes. The magnitudes of the earthquakes range from about 1.8 as an aftershock to the main shock of 2.6, and there was a foreshock prior to that. About an hour and a half, a little less than 90 minutes after the last earthquake, the Fundao tailings dam failed. There's a number of eyewitness accounts of these earthquakes, some of which are presented on this slide. One account is that the shaking was strong enough to cause a computer to fall off a tabletop or desktop and cause minor structural cracking in the building that this person was sitting in. Another person was on the dam during the second shock or earthquake, and that shook this person's truck enough for her to recognize it clearly. Another eyewitness account of their desk shaking and glass being broken. So if you use those eyewitness accounts, you can estimate a modified Mercalli index of about, or intensity, of about 5 to 6. And then you can relate the modified Mercalli intensity to magnitude through various scales, which is done on this slide. So if you look at the modified Mercalli index for 5 and 6, it says felt outdoors, small unstable objects displaced or upset, and that's for a MMI of 5. 6 is felt by all, and it was what these earthquakes were widely felt. Furniture moved, weak plaster / masonry cracked. So we think that a modified Mercalli intensity of about 5 to 6 is representative, and that corresponds to a Richter magnitude of about 4 to 5. We also use the pore pressure generation, which I'll be presenting in just a minute, to sort of perform an inverse analysis of the magnitude and got a similar range of Richter magnitude of between 4 and 5. So with that background on the earthquakes, I want to shift to the dam and the instrumentation that was available. The dam was actually highly instrumented. There were 116 piezometers and water level indicators within the starter dam as well as the raised portion of the dam. The tailings dam was constructed using the upstream method after construction of the starter dam to elevation 826. The blue dots in the photograph are the piezometers and water level indicators, so you can see a significant density. And two cross sections that I'm highlighting are BB and 02. Our analysis is going to focus in on 02 in just a minute. But the failure started on the left abutment, which is over by cross section 02, and this slide gives some insight to why the left abutment was less stable than the right abutment where BB is. The plot underneath the photograph shows the piezometric level from the right abutment towards the left abutment. And it shows that the piezometric level was much lower on the right abutment than the left abutment. So there was a higher static pore pressure ratio, RU, on the left abutment than the right abutment. Another feature I want to emphasize in the plot of piezometric level are the two yellow lines. The yellow line closest to the right abutment is the elevation 826 blanket drain, and the yellow line on the left abutment, or near the left abutment, is the 860 blanket drain that was under construction or just completed at the time of failure, and that's the topic of the next slide. This slide shows the 826 drain in yellow, and so when it was constructed at roughly the top of the starter dam, it covered the full width of the dam and provided drainage to the piezometric level within the tailing storage facility, or TSF. As the dam moved upstream via the raising method, the axis moved off the 826 drain, and that's why in the lower right you can see the second yellow area going in as the 860 drain, which was under construction at the time, or just completed at the time of the failure. And the axis of the dam was going to move back on top of the 860 drain if the dam had not failed. So here's our cross-section 02 that we're going to focus on for our dynamic analysis. These blue dots on this slide illustrate locations of cone penetration or standard penetration testing and borings that we are going to use to assess the liquefaction resistance or pore pressure resistance of the materials involved. A couple important geometry aspects of cross-section 02. Notice there's a flat portion near the bottom of section 02. That's called the plateau. And then the upstream raising method takes the dam from the plateau area, roughly 860, up to the height of the last raise at the time of the failure at elevation 902, or about 40 meters. Here's a cross-section through 02, and the top of the raising at about elevation 902, the plateau at about elevation 860, and we broke the analysis up into 3 zones: the downstream slope, or what's on this figure called sand slope, the plateau area, which is the sand plateau in the middle, and then the toe of the plateau area, which we've called the sand toe. And so notice there's a CPT 0.6 in the downstream slope area, and that's going to be used in this pore pressure generation analysis for the sloped area. On the plateau, there is SPT data in FUND 15, and that's going to be used for pore pressure generation below the plateau. And finally, a CPT at the toe, Fundao 16, that will be used for the toe of the plateau area. So I'm going to start with the downstream slope, and that's sand slope. There's the CPT on the bench at roughly elevation 875 on the downstream side where the CPT was pushed, and the plateau is just downstream of it, or downslope of it. Here's the CPT data from Fundao 06 CPT, and you can see the piezometric levels occurring at about elevation 868. And so this pink zone that's highlighted is the area of saturation and also low CPT tip resistance. So our pore pressure generation analysis is focusing in on this area between 868 and say 865, where it's below the piezometric level and the lowest CPT data. We didn't focus in on this lower CPT data at elevation 862 because it's a little deeper than this loose zone near the surface. Plus the field observations, which I'll talk about in just a minute, indicate that the plateau was moving, and so we focused in at 868. Okay, here's the site response analysis for the downstream plateau or slope area, and this is a plot of peak acceleration or maximum acceleration versus elevation. There's the pink zone that we're focused in on for the pore pressure generation analysis, and the green dots or squares are for the foreshock and aftershock because they're similar. And the main shock is the red triangles, and so you can see the acceleration amplified a little bit from the bedrock up to the surface of the downstream slope. Those accelerations are used in the pore pressure generation analysis that I'll show you in just a minute. So here's the CPT data on the left, tip resistance, and on the right is the factor of safety, or basically the ratio, the seismic cyclic stress ratio and the cyclic resistance ratio. We use the ratio of these curves, so the ratio of CRR, which are the black circles, to the CSR, cyclic stress ratio, induced, to estimate the factor of safety against liquefaction. So the green line is for, or the green dots are for the foreshock and the aftershock. So you can see that those points yield a factor of safety against liquefaction of about 1.6 above the pink zone. The main shock, which are the red triangles, taking the ratio of CRR to CSR, yields a factor of safety against liquefaction of 1.1 approximately. The importance of those factors of safety against liquefaction are twofold. First, there wasn't a triggering of liquefaction by any one event, but the 3 events occurred within 4 minutes, and each of those events had a duration of a minute or greater. So it was basically continuous shaking for 4 minutes. So we can use those liquefaction factors of safety to estimate the pore pressure generated during each event. And that's the second use of the liquefaction factor of safety. So we used a couple relationships, one of which is this one by Marcuson et al., 1990, where you can enter the graph as a function of the factor of safety against liquefaction and then estimate the excess pore pressure ratio, RU, which is the pore pressure divided by the total stress, or gamma H. So coming in with a pore pressure, a factor of safety against liquefaction of 1.1, you can read up the vertical axis and estimate the RU value that was induced during the main shock. And that was what is shown on the prior slide. If you see underneath the factor of safety 1.1, there's an RU of 0.5. For the factor of safety of 1.6 with the foreshock and aftershock, the factor of safety is 1.6, and that leads to an RU of 0.2 only. Okay, so if you are interested in the calculations, they are shown on this slide, and I'll be happy to provide the slides if you're interested. So this is the slope, the downstream slope area, tailing sand slope at a depth of 4.25 meters for the main shock. There's our cone tip resistance, our fines content correction, the alpha and K alpha value, because it's on a slope, there's a static shear stress that's applied, and we have to incorporate that into the resistance. And then at the bottom is the factor of safety against liquefaction during the main shock, and you can see it's about 1.1. So liquefaction did not trigger, as we're accustomed to saying, but it, using empirical relationships, it did generate pore pressure during the main shock. So the next slide shows the calculations for the foreshock and the aftershock, which were about the same, also at the same depth of 4.25 meters. Notice the factor of safety against liquefaction is now 1.6, so the RU is much lower at 0.2. But that's the cumulative buildup of RU during these 3 earthquakes. Now, please remember that the piezometric level is higher on the left abutment than the right abutment, so the static level of RU was 0.17. So these excess pore pressures during the earthquake are added to the static RU value of 0.17, and I'll show you that in the table, and that will lead to the application of a liquefied strength to the slope area and the toe area. Okay, so does these calculations of factor of safety against liquefaction and pore pressure buildup make any sense in relation to the field observations? So these next 2 slides illustrate some of the field observations of people, workers at the site, and what they felt and observed during these 3 earthquakes. The numbers that are below in the text correspond to the numbers in the photograph, and they indicate where that particular employee or worker was located when they made this observation. So, for example, observation number 1 is on the plateau. Worker standing on the plateau felt it begin to move beneath him and crack around him, detaching from the setback slope and moving downstream, indicating a shallow failure in around the plateau area. 2, 3, and 5, the failure occurring from bottom up. Next slide illustrates no movement in the starter dam. Basically, the movement was above the starter dam, which is just below the plateau area. So with those observations, we continued, and here's the sand plateau analysis using blow count data in the plateau area. Same estimate of factor of safety against liquefaction. Notice the factors of safety are above 2. For the foreshock and aftershock, 2.9, and for the main shock, 2.1 to 2.2. So a much lower buildup of pore pressure in the plateau area, an RU of 0.07 and 0.11 during the main shock. So to skip to the result for the plateau is liquefied strength will not be applied in the plateau. Here's the toe of the plateau area where a CPT is located, and that's where the red arrow is shown on this photograph. Same analysis, factor of safety against liquefaction varies from 1.9 for the fore and aftershock, 1.4 main shock, and the pore pressure ratio generated is 0.1 to 0.3. So what is happening during the earthquake is, if we plot it on a critical state line, it started to the right of the critical state line at the initial point. Pore pressures built up because the earthquakes occurred in 3 minutes, 3 earthquakes in 4 minutes, no time to drain pore pressure, and so the effective stress decreased during each of the events until it crossed the critical state line for the slope area and the toe area, and thus we applied a liquefied strength in those 2 areas. The criteria for applying the liquefied strength was an RU, a total RU of 0.7 or greater. So that brings me to the slope stability analysis. There's the cross section that I started with, the static value of RU of 0.17, using the pore pressures generated through the 3 earthquakes. Notice the RU for the slope is about 1, indicating a liquefied strength condition. The toe, 0.73, indicating also a liquefied strength condition. But in our slope stability analyses in the plateau area, which is the light blue area, the RU is less than 0.7, so the strength was not reduced from the value estimate, the friction angle estimated using the blow count data. So the strength parameters used in the analysis are summarized on this table. So notice the sand toe and slope are applied a liquefied ratio of 0.03, but the plateau area keeps a effective stress friction angle of 22 degrees, but the pore pressures generated are included. So here's the factor of safety with time. Before the earthquake, the failure surface that we analyzed based on field observations of cracking on the slope and at the toe was up over 3. The foreshock reduced it to about 2.8. The main shock reduced it to about 1.6. The aftershock down to about 1.2 to 2.5. And then at this point, between 216 and the failure in 345, a liquefied strength mobilizes for the slope area and the toe area, and that drops it, the factor of safety, to 1, and thus the failure. In summary, tailings dam stability should consider dynamic loads and dynamic forces such as blasting and earthquakes or any other dynamic event. The Fundao tailings dam failure, we believe, was caused by an accumulation of excess pore water pressures at shallow depths on the downstream side in the slope below the 875 bench, the plateau, and the toe. That started a retrogressive slide that moved up towards the top and then finally led to a breach of the TSF. This is not occurring at a large depth. This is within a depth of, say, 3 to 6 meters below the surface, not at large depths, because at large depths the total stress is extremely high, and thus the pore pressure ratio is smaller. Finally, tailings dam failures usually result in a large environmental impact, and so stability analyses should be done carefully, both considering static and dynamic loads, such that a failure does not occur. So with that, let me check to see if I got any questions. Nope, no questions. So,
Tim, this is Scott. I have a question if you're open to that.
sure, please.
Tim, one of the challenges that we've faced in the Army Corps of Engineers as we're implementing risk-informed processes is that we've found that a lot of our engineers are influenced by what the National Academy refers to as confirmation bias. And one of the problems we've seen in the engineering development area is that oftentimes we'll see analyses which allegedly prove something, and yet when we look back at it in retrospect, what we find out is that we didn't really actually apply the scientific method, which is not to prove a hypothesis, but rather to try to disprove it. So my question is, this is a very interesting analysis. I find it neat and compelling and plausible. But what sorts of things do you think we need to do to try and disprove these various hypotheses to come to a fuller understanding of the mechanisms that are causing these kinds of failures?
Great question, Scott. And let me just, given a short period of time, let me just focus on Fundao. You know that there are other things happening right now. But so that's exactly what we did. As you know, there are other hypotheses out there for this particular event. We assessed those and applied the scientific method, and we did not think that a mechanism at a depth of 50 to 60 meters was really plausible for it, especially given the field observations that indicated the movement and pore pressures were being generated at shallow depths, which makes sense because the total stress is lower. So that's how we ended up actually at this pore pressure generation mechanism, because the other hypotheses didn't really seem to explain the field events. So I think, to answer your question directly, start with the field observations. Whatever they are, follow them as far as you can and make sure the analysis model the field events.
Very good. Thank you, Tim. It was a very interesting presentation. I'm serving as your forum moderator, and I want to thank you for a very nice presentation.
Great, Scott. Thanks. So I'll wrap things up. Recordings of all today's presentations will be made available on YouTube. If you would like a PDF of the slides, please contact the presenters, and their email address was on the slides, or if you just Google them, that'll show up. The last EDS web conference is tomorrow at 10 a.m. The 4 speakers in this event are Thomas Uman, who will talk about remote sensing for slopes and embankment, Nevin Matasevich, who will talk about seismic stability, Jay McKelvey, who will talk about reinforced slopes, and Ada Zekos, who will talk about the performance of levees. Finally, I'd like to thank today's speakers for their excellent presentations and our gold sponsor, Keller, for supporting our web conference, all 3 of them. We really appreciate their support for this event. So thank you all for joining us, and if you have questions or would like the PDF, please email the speakers, or you can email me and I'll contact the speakers. Thank you for attending, and I hope you'll attend tomorrow's session at 10 a.m. Thank you.